Okay, hi guys. Here today we're going to try to pick up where we left off yesterday. A little bit of this first part is a review, especially after you've done problem set 19.1. So we'll go ahead and talk about the concentration of H plus and OH minus in solution, and then we're going to introduce titrations. Titrations will be part of the next problem set 19.2. Unfortunately, with Explain Everything, when I pull your PowerPoint slides in, it doesn't bring over my subscripts and superscripts. So understand that this reaction that you see here is H plus hydroxide making H2O. So if you add to this system, which is just water, if you add HCl, you're adding more of the H plus concentration, and you're also adding chloride. Now chloride's not going to have any effect on the acidity or basicity of this solution. So you can calculate the H plus concentration or the OH minus concentration if you knew how much HCl you had added. In this case, you simply know you added more H plus, so the concentration of H plus goes up. Because if you make more H plus available in solution, it will react with the hydroxide ion that you have there. You'll produce more water, and the system will rebalance itself. When that happens, the hydroxide ion concentration actually goes down, because if you remember, Kw is H plus, concentration of H plus, times the concentration of hydroxide. So if one of these goes up, the other goes down in order to maintain a constant value of Kw. So at 25 degrees, Kw is 1.0 times 10 to the negative 14th. We consider acid substances that produce more H plus when they're in water and when they're ionized. So the amount of H plus is greater than the amount of hydroxide if the solution is acidic. If you remember your pH scale, most of you have heard about it. We typically have a pH scale that goes from 0 to 14. Sometimes you've heard of it going from 1 to 14. It actually goes from 0 to 14. And anything down here from 0 to 7 is considered an acid. And anything between 7 and 14 is considered a base. The pH of 7 right here, that would be a neutral solution, which is the same thing as pure water. So an acidic solution has more H plus ions, and it also has a pH that's below 7. Now our same reaction that we had before, where we have H plus hydroxide making water, if we add a base to this, immediately we get ions as the base dissociates. So you're adding Na plus concentration and hydroxide. So this does not affect our H plus concentration initially. We have hydroxide ions that are dumped into this system, so there's a lot more hydroxide. And as those hydroxide ions react with the H plus ions, we produce more water. So the concentration of H plus goes down. Again, I remind you that H plus concentration times hydroxide ion concentration equals a constant number, and that number doesn't change. So if hydroxide ions go up, if that concentration increases, concentration of H plus decreases. I feel like the slides here might be slightly out of order compared to your note packet. I'm working from home with an older version. So if we have a system right here where we have a certain number of moles of NaOH dissolved in a particular volume of water, we're looking for the H plus concentration and the hydroxide ion concentration. So we start off with the hydroxide ion concentration because we know this. We know that in this system there's 0.010 moles, and this is dissolved in a 1.00 liter solution. So we can figure out the molarity is 0.010 molar. That's the concentration of hydroxide. We can now take and figure out the concentration of H plus, but we have to go back to our Kw equation. So we know that Kw equals the concentration of H plus times the concentration of hydroxide. We know the concentration of hydroxide. We know the value of Kw. We can solve for H plus. So Kw divided by hydroxide ion will equal our H plus. So Kw is 1.00 times 10 to the negative 14th, and that's divided by 0.010 molar. You calculate this out, you get 1.00 times 10 to the negative 12th, and that would be molarity. This is equal to the concentration of hydroxide ions. Oh, nope, it's not equal to hydroxide ions. It's equal to H plus. So bases have a greater presence of hydroxide ion when they're in solution. Therefore, the amount of H plus is lower. So again, on the pH scale, bases are above pH 7, up in this area. Now, pH 7 is equivalent to an H plus concentration of 10 to the negative 7. And pH 14 is equal to a concentration of 10 to the negative 14th. We can also figure out the hydroxide ion concentrations. So when something is neutral, hydroxide ion concentrations are also 10 to the negative 7. But over here, the amount of hydroxide ion is much lower. So this would equal 10 kW. I'll just write this out. It'll equal kW divided by H plus. So you can always figure out the concentration of H plus or hydroxide at any point along the pH scale. We'll actually calculate pH and pOH and do more of those calculations probably tomorrow. So just to recap, a solution that's neutral has equal amounts of H plus and hydroxide ion with a pH of 7. An acidic solution has more H plus with a pH that is lower than 7. And basic solutions have a greater amount of hydroxide ions for a pH that is greater than 7. We're going to begin to talk about acid and base neutralization. So whenever we mix an acid and a base together, we make water and a salt. This is really just another example of a double replacement reaction. So the sodium and the hydrogen ions are going to switch places. So our product in this case is NaCl and H2O. Remember that H2O can be written as HOH if that is something that you prefer. This particular equation is balanced. All acid-base neutralization reactions have water as a product. So I can have a different acid that's reacting and a different base that's reacting. And here I would produce magnesium nitrate, which does happen to be a salt. That's a metal with nonmetal or a polyatomic ion, and HOH. So to balance this equation, we'll need 2 of the nitrate ions, and we'll need 2 water overall. So this reaction right here, with phases, is an acid-base neutralization reaction. Now, we've been using the definition called an Arrhenius acid when we're talking about acids and bases. And an Arrhenius acid says that hydrogen ions are released. That's the definition. So any acid in the Arrhenius model has to have hydrogen. Any base in the Arrhenius model has to have hydroxide. So as we go along in this unit, we'll actually broaden our definitions a little bit and start looking at other examples of acids or bases that don't necessarily involve H plus or hydroxide. So keep that in mind. Right now we're working with that Arrhenius model, so it's Arrhenius. Yes. And I know that that's hard to read, but I do believe that that's in your note packet. I'm pretty sure this part is actually in your note packet also. I'm not sure that I'm going completely in order. So feel free to pause things and figure out where you're supposed to be. What we're looking at right now is if we take acid and base and we mix them together in the same solution, except we have more acid than we have base, what happens to the solution? Is this a low pH, is this a high pH, or is it neutral? So we can figure all of that out if we know how much is added. So here we have sodium hydroxide, and we know the number of moles. So our hydroxide ion is going to be equal to 0.090 moles divided by 0.100 liters. So our concentration of hydroxide is 0.90 molar. And then we're going to figure out our H+. So our H+ concentration, at least right off the bat, is 1.0 molar. Oops, it's hard to see. So what happens? What happens in this reaction? Take just a second. You probably need to move and talk. Pause the video and ask your neighbor what happens in this solution. Okay, well, I hope that you came up with the idea that at least some of the hydroxide and the hydrogen ion will react together and make water. And so to show that, we use something called an ice chart. So we know that H plus hydroxide ion makes H2O. And we're saying that we're starting this reaction with 0.90 molar hydroxide, and we have 1.0 for H plus. So basically the smaller of the two amounts will neutralize and react with the other one. So in this example, I have approximately 0 hydroxide ion. We know that that's actually not true because water always self-ionizes. So no matter what, there's always a little bit of either H plus or hydroxide ion that's present in the solution. But here we have an amount of 0.1 molar hydrogen ion rather. So in this example, you have excess HCl. You have more H plus that's left over in the concentration in the container. And so we can make the conclusion for this one that the pH will be less than 7. After we talk about how you calculate pH, pH is actually calculated by the negative log of the hydrogen ion. We could figure out the exact value. Now we're going to look at an example that has excess hydroxide ion. So here we have 0.101 moles divided by 0.100 liters. And so that tells us that we have 1.01 molarity of hydroxide. So if we set up our ice chart, H plus hydroxide, and we say that we have 1, and really truly in this ice chart we should be using moles, not molarity, but it'll be okay for this one. So we have 1 of H plus and we have 1.01 of hydroxide. So the smaller of the two amounts will neutralize the other and react. So 1.0 reacts with hydroxide, and we have approximately 0 concentration of the hydroxide ion. Again, I emphasize to you that it's not really 0. So here we have 1.0 that reacts, and we're left with 0.01. This is the molarity of the hydroxide ion, and we could take this a step further and figure out that the pH will be greater than 7. As you can probably expect, if we have exactly the same amount of hydroxide ion and exactly the same amount of hydrogen ion, if there's no excess of either, then our pH is equal to 7. We don't have to do much more with this at all. When we come back from break, one of the first things that we do will be titrate. So titrate is the process of adding an acid to a base or a base to an acid and trying to figure out the concentration of one or the other. In our lab, we're going to know the concentration of the acid, we'll know the volume of the acid that's added, we'll be able to figure out the volume of base that we use, and we'll be trying to solve for the molarity of the base. So this is a pretty standard process. Titrations are used extensively in general chemistry, and actually they're really used in industry. Sometimes you titrate things just to verify how much is there. And titration is always based on the idea that the moles of H plus ions equal the moles of hydroxide ions. That this is considered equivalence, and we'll talk about this again on the next slide. But this is what frames titrations. You figure out how many moles of one or the other you have, and you can solve the rest of the problem. So here's a fairly standard titration question. You can see that we have the volume of NaOH, we have the volume of HCl and the molarity of HCl, and we're looking for the concentration of the sodium hydroxide solution. So we are going to keep in mind that the moles of hydrogen equal the moles of hydroxide. So the first thing we're going to do is we're going to use the volume of HCl and the molarity of HCl to find the moles of H+. So moles of H+ will equal 0.100 molarity times the volume in liters. And so this is 0.0100, right, that's it for sig figs, that's liters. So we're going to multiply 0.0100 liters. So our number of moles is equal to 0.00100. And this is moles of H+. So we know that that also means that if it's neutralizing and we have one hydroxide for every one H+, that moles of hydroxide ion equal moles of H+. So we can make this step right here. Okay. And then, if we know the volume of the NaOH that's given to us, the concentration of the hydroxide is equal to moles divided by the volume in liters, 0.015 liters. Okay, so this is 0.0632 sig figs, 3 sig figs, that's a 0 right there. 6, 7, and this is molar. So that's my concentration of hydroxide. Because sodium hydroxide only has one hydroxide ion, it's also the concentration of the original sodium hydroxide. So we're going to spend a little bit more time on this, and we're going to look at the nuances of titration. So I've emphasized a couple of things here that you won't catch the first time through, and as you go through and practice more and more, you'll get more of these pieces. Okay, when you do a titration, you do want to remember that at equivalence, essentially at neutralization, moles of hydroxide do equal moles of H+. We will use an indicator that changes color with pH. The one that we'll use tomorrow is phenolphthalein. So PHENOLPTHA, phenolphthalein. I think that I spelled it right. I know it doesn't look like it. There might be an extra T or H in there that I missed. But phenolphthalein is an indicator, a compound, that turns pink in the presence of hydroxide ions. And it is colorless in the presence of H+. So it's very, very useful. Excuse me. The endpoint is actually that point where the indicator changes color. So in an ideal situation, the equivalence point and the endpoint match. I would actually like you to work through the next couple titration example problems. Here's one, and I don't want to do it for you. I'd like you to do it. In this particular problem, you're going to solve for moles first. I would solve for moles of HCl, which is actually moles of H+. Then you're going to set that equal to hydroxide, and then you'll figure out the concentration of KOH. Now this problem, I want you to be careful about the hydroxide, because you'll notice that you have calcium hydroxide and there are two hydroxide ions. So you have to be extra careful. There's a mole ratio here that you have to pay attention to. So the first thing you'll do is you'll solve for H+, then you'll set that equal to hydroxide ions. But then you need to do a mole ratio. So this one we'll actually do together. So to solve for moles, we do 0.200 molar times 0.0140 liters, and that gives us, see if your teacher can do this in your head. No, she can't. That gives us 0.00280 moles of H+. So that's equal to the number of moles of hydroxide ion. But in 1 mole of calcium hydroxide, there are 2 hydroxide ions. So I'm actually going to multiply by a mole ratio. It says that for every 2 moles of hydroxide ions, I get 1 mole of calcium hydroxide. And so we divide this by 2, and we get 140 moles of calcium hydroxide, because remember, calcium hydroxide comes with the hydroxide ions in like packages of 2, like they come in a pair here. And our final step is to divide this by the volume, that is in milliliters, so we convert it to liters, 0.183, and that's in liters, and we will solve that. So our answer here is maybe I can write the answer. The answer here is 0.0765, and that's molarity of calcium hydroxide, because that's actually what the question was asking. Final example problem is another fairly straightforward titration problem, except it gives you moles. It doesn't give you molarity and volume. You can start right there. Basically, you skip a step.